So let's continue our discussion of ideal gas behavior. Let's look at a few example questions. Here's one. What's the final pressure of the gas originally at 30 liters, 250 torr, if it's compressed to 15 liters at constant temperature? So what's applicable here? PV equals nRT. What's being held constant? You have a fixed amount of gas, temperature is constant, so PV is a constant, so Boyle's law is applicable here. So you say P1 V1 equals P2 V2, and we're looking for final pressure, so I can solve for P2 is P1 V1 over V2. What's my P1? 250 torr, and my V1 is 30 liters divided by V2 is 15.0 liters. You cut the volume in half, and you expect the pressure to double, right? So it's 500 torr. Correct answer is B. How about this one? If the pressure of a gas is tripled at constant temperature, what happens to the volume? So PV is a constant, right? So if you multiply this by 3, how will the product remain constant? You multiply the volume by 1/3. So the volume is reduced to 1/3 of its original volume. How about this one? Volume of a gas decreases from 8 liters to 2 liters at constant temperature. So what will happen to the pressure? From 8 to 2, that's multiplied by 1/4, right? So if your volume shrinks, you expect your pressure to increase. So it's not going to be reduced. It's going to be quadrupled. So whatever your original pressure is, you're going to be multiplying it by 4 to get the final pressure. So A would be the answer. The pressure would be quadrupled. How about this one? PV isotherms shown below. One represents high temperature data, the other one's a lower temperature for same sample of gas. Which one would be a higher temperature, T1 or T2? T1, right? And here's a way of looking at it. Let's say you want to do this one. P1 V2, okay, is equal to nRT2. Let's call this V2 right here, right? And P1 is the same as P2. V1 is nRT1. That's one way of looking at it. Okay. So which one is larger, P1 V2 or P1 V1? P1 V1 is larger. That means if P1 V1 is larger, you have same N, same R, then that means T1 must be larger. Okay? So this is a higher temperature isotherm. How about this one? Final volume of a gas, initially at 25 liters, 25 degrees Celsius, heated to 50 degrees. So temperature went from 25 to 50, constant pressure. So which law is applicable here? Charles's law. Volume and temperature are directly proportional. It's equal to nR over P, which is a constant. So what do you think is going to happen to the volume? From 25 liters, it's going to shrink or increase? You raise the temperature, so it's not going to shrink. It's going to expand, so it can't be 12.5. Is it 27.1 or 50? The temperature did not double. The Celsius temperature reading doubled, but the absolute temperature did not double. So you don't expect the volume to double here. Okay, so what happens here? We have 20, so V2 would be equal to 1. All right, let's see. You're right. V1 over T1 equals V2 over T2. So I solve for V2. V2 is equal to V1 times T2 over T1. So what's our initial volume? 25 liters. And our final temperature is 50 plus 273.15. And our initial temperature is 25.0 plus 273.15. So your temperature has to be in Kelvin. And so this should only give you 27.1 liters. Okay? He did not double the volume. He did not double the temperature either. How about this one? That's the final volume of a gas, initially at 30 liters, 250 torrs, 25 degrees. If the pressure and temperature are changed to 500 torr, so you increase the pressure, that would cause the volume to shrink, all other factors being the same, right? But you raise it from 25 degrees to 115, so other factors being the same, it's going to cause the volume to expand. So you're changing two things here. The only constant here is the number of moles. So which law would you use here? Combined gas law. So you can say P1 V1 over T1 equals P2 V2 over T2. In fact, that's equal, both of those are equal to NR, right? So you could actually solve for N. You have enough information to solve for N if you want to do it that way. You solve for N and then you plug it back into the other equation. But since you're not really interested in N here, what do? You just say, what are we looking for? Final volume. So V2 is the initial volume times T2 over T1 times P1 over P2, right? So rearrange that equation. So what's our initial volume? 30 liters. What's our temperature? Final is 115. So that's 115 plus 273.15 divided by initial temperature is 25. So 25 plus 273.15. What's our final pressure? 500 torr. 500 torr goes down here. Initial pressure is 250. Okay. And what should that give you? $30 times 115 plus 273.15 over 25 plus 273.15 plus 273.15 make that big. And that plus is really small. Times 250 over 500. That gives us 19.528. So So the answer is 19.5. Big sig things. Okay. All right. About counting gas particles, number of moles. When we use the word particle, okay, we can use that as a generic way of referring to each molecule. A molecule, if you remember, is two or more atoms bonded together, right? And or when you have a gas, it's either you can either have molecules in there or unbonded atoms. So just to be generic, if you want to refer to the particles in your to the atoms and the molecules in your sample, we'll refer to them as gas particles. Okay, and in your equation PV equals nRT, that N actually represents the moles of gas particles. So as far as counting gas particles are concerned, a molecule counts the same as an unbonded atom. Okay, so a free atom counts as one particle, and a molecule counts as one particle as far as that N is concerned in your ideal gas equation. So if you are going to compare 1 mole of CH4 and 1 mole of helium, they both have N equals 1 mole. Okay, even though CH4 has actually what? How many moles of atoms does CH4 actually have? 5, because each molecule has 5 atoms. But as far as using the equation PV equals nRT, the N there refers to the gas particles, where molecules and atoms are treated the same way. Each one is treated as one particle. All right. So if you measure the pressure, volume, and temperature of a gas, okay, like I said, you can use the ideal gas equation to solve for the number of moles of gas particles. It doesn't matter whether they're molecules or atoms. They're going to be counted the same way. So for salt, okay, and like I said, PV equals nRT is only valid at low pressures. Under ordinary conditions, we expect, if we use this equation, we expect to be in error by about 1%. And the units that we have to use for our constant R has to depend on what unit, depends on what unit we use for pressure, volume, and temperature. So if you use liter for volume, atmosphere for pressure, then the value of R is 0.08206 liter atmosphere per mole per Kelvin. Okay, and let's see where that unit comes from. R is PV over NT, right? If you rearrange PV equals nRT, so you need a pressure unit, so atmosphere, times a volume unit times liters, divided by a unit for mole, for N, which is mole, and a unit for temperature, which is Kelvin. So you can see that's your unit for R. So if you want to memorize one number, the one that was recommended to you in your freshman chemistry class was 0.08206, and if you memorize that number, then whatever pressure values you have, you just change it to atmosphere. Whatever temperature you have, change it to Kelvin. Whatever volume you have, you change it to liters. And you can ensure that you have consistency when you do your calculation. Okay? Now, since we're going to be using more SI units, you need to be familiar with this other number here. 0.08314 is what you get if you use liter bar per mole per Kelvin. If you remember, what was a bar? A bar is 10 to the 5th pascals, right? A liter bar is in fact related to a joule. Okay, the SI unit for pressure times volume. Okay, what's the SI unit for pressure again? Pascal, and then the SI unit for volume is in fact cubic meters, right? So a Pascal is a Newton per square meter, and a cubic meter is a cubic meter. What happens if you multiply these two? Meter squared and meter cubed cancel out, so you just have a Newton meter. What's a Newton meter? That's a joule. Okay? So you'll notice these digits here, 0.08314 is the same digits here, 8.314, but this is joules. Okay, so you can see that 1 liter bar is in fact 100 joules. So a liter bar, so a liter atmosphere, a pressure unit times a volume unit is actually a unit of energy. Okay, so a liter atmosphere, you can say 1 liter atmosphere, 1 liter times atmosphere is 1.01325. You've seen this number before, right? 1 atmosphere is 1.01325 bar. 1 liter atmosphere is 1.01325 liter bar. Okay? Or that's 1.01325 times 10 to the 2 10 joules. 101 joules. Okay? 1 liter atmosphere is 101 joules. So these are numbers that you should be familiar with because we do use a lot of SI units in our calculation. So a liter bar is 100 joules. A liter atmosphere is 101.325 joules. Yes? Oh, down here? Oh, this is the same thing right here. 1 liter bar is 100 joules. A 1 liter atmosphere is 101.325 joules. Okay. Okay, so let's calculate the number of moles of gas particles as present in STP. You've encountered STP in your freshman class. It's defined as 273.15 Kelvin. That's the freezing point of water, or the melting point of ice, and 1 atmosphere. Now, another acronym you might encounter is called Standard Ambient Temperature and Pressure, SATP. This is what we would call ordinary conditions in the lab. Typically, you would set the lab at 25 degrees Celsius, so 298.15 Kelvin, and this uses 1 bar as a standard pressure. Okay, so what would be the volume of a gas at STP? What did you remember from freshman chemistry? 1 mole of gas at STP, what's the volume? Let's calculate. Volume is nRT over P. If you have 1 mole, what's our R? Let's do it in liter atmospheres. 0.08206 liters atmosphere per mole Kelvin. And what's our temperature? 273.15. Okay. I need more room here. Let me see if I can fix this up. Oops. Let me do it down here. So 1 mole times R is 0.08206 liters times atmosphere per mole per Kelvin. Our temperature is 273.15 Kelvin. And our pressure is 1 atmosphere. And you'll find that this is 22.4 liters. So we say that the molar volume, the volume of 1 mole of gas at STP, if it obeys the ideal gas law, is going to be 22.4 liters. So you can actually use that as a conversion factor to calculate moles from volume, provided your gas is at STP. Okay. Now at SATP, you're going. So this is at STP. Okay. Volume per mole, molar volume, also sometimes written as V bar, is 22.4 liters per mole. Okay. What would be the molar volume at SATP? If you did the calculation, this is a good number to remember, 24.8 liters. So about 25 liters. So 25 liters is the molar volume at SATP. Standard ambient temperature. So if I gave you a 2-liter empty bottle of Coke, and I asked you how many moles of air particles are in that empty 2-liter bottle of Coke? What would it be? Let's assume the Coke is not in the refrigerator. It's sitting on your countertop at room temperature, 298 Kelvin. What's the answer? You got a number for me? Point 0.082 moles. Let's see. You have 2 liters times 1 mole at SATP is how much? About 24 liters, 24.8 liters. So 2 out of 25, 1 out of 25 is 0.04, right? So 2 out of 25 would be about 0.08. So that's about right. Okay? So that many molecules, that many particles of air in your 2-liter sample. So what would that actual number be? So if it's 0.082 moles multiplied by Avogadro's number, 6.02 times 10 to the 23rd molecules per mole. We can assume most of the particles in air are molecules. They're O2, 20% O2, about 80% N2. Okay? So let's multiply that by Avogadro number. That gives you the actual number of molecules. Okay. So Avogadro's law, as I mentioned earlier, says that the molar volume of a gas at constant temperature and pressure is a constant, and you can see that this law is incorporated in that ideal gas equation. Okay, so if you rewrite this ideal gas equation, V over N, that's the volume of 1 mole, volume per mole, is just equal to RT over P. So if temperature and pressure are fixed, the molar volume is fixed. So what is it at STP? 22.4 liters per mole. What is the molar volume at standard ambient temperature and pressure? 24.8 liters per mole. Okay, so V over N is a constant. Okay, so what this means is you can use volume, as we've illustrated earlier, as a way of counting your molecules, your particles in your gas sample. So more moles of gas, you have bigger volume. Smaller moles of gas, smaller volume. So you can also use, say, V1 over N1 equals V2 over N2 at constant temperature and pressure. Okay, so it's 22.4 liters per mole, 24.8 liters per mole at SATP. Now, here's a good number to memorize because we're going to be using these numbers a lot. You'll see this RT expression a lot in our calculations. Now, since PV equals nRT, okay, one thing you'll notice, if you solve for RT, what would you get? RT is equal to PV over N, right? So at STP, what is RT at STP? 1 atmosphere. What's the volume at STP? 22.4, right? And for 1 mole, right? So this is 24.4 liters per mole. So you can see that RT is equal to 22.4 liters per mole, liter atmosphere per mole. Okay. Now, a more useful value for RT is at SATP. So at standard ambient temperature and pressure, what's our pressure? 1 bar. And what's our volume? 24.8 liters. Right? What's our number of moles? 1 mole. It's 24.8 liters per mole. So RT at room temperature is equal to 24.8 liter bar. This is a very good number to remember because when we do a lot of these calculations, we encounter RT a lot in our formulas. So 24.8 liter bar, or since a liter bar is 100 joules, okay? So 24.8 liter bar, and 1 liter bar is 100 joules. That gives you 24,800 joules, or 22.48 kilojoules. 2480 joules, right? Or 2.48 kilojoules. So that's the value of RT at room temperature. It's about 2.5 kilojoules. Okay? So that's a nice number to remember because, like I said, you'll see that a lot when we do our calculations in thermodynamics. RT at room temperature is about 2.5 kilojoules. All right, so let's do a quick review. Which of the following gas samples contains the most number of gas particles at the same temperature and pressure? A, B, C, or D? 2 liters of CH4, 1 liter of H2, 2 liters helium, 4 liters of helium. They have the same temperature and pressure, so what do we know about same temperature and pressure? What law is applicable? Avogadro's law, right? Volume is directly proportional to the number of moles. V over N is a constant, right? RT over P. So how can you tell which one has the most number of particles? Use of volume. So the answer is D. Okay? Now, which one has the most number of atoms? Okay, let's compare it with A and D. D would have twice as many moles of particles, but each particle in sample D is just a single atom, whereas each particle in sample A is a molecule that's made up of 5 atoms. So what wins out? A. Okay, so A has more atoms, D has more particles. I think that was the next question. Let's talk about partial pressure. Partial pressure is something we deal with when we're dealing with mixtures of gases. Now, for any gas, whether it's pure or a mixture, if the ideal gas law is applicable, then PV equals nRT is applicable, and N is just the count of the total number of gas particles regardless of what kind they are. So it doesn't have to be a pure sample of gas. It can be different. You can have mixtures of different kinds of molecules and atoms there. So let's just rearrange this equation to solve for P. What do we get? It's going to be nRT divided by the volume. That would be the pressure of your sample, where N is the total number of particles. Now we can define partial pressure as the pressure that a component of a gas mixture would exert if it were alone. So let's say you have a gas as a mixture of molecules A, B, and C, and so on. Well, if you just count the number of molecules of A, multiply that by RT over V, if you ignore all the other molecules that are there, then N sub A, number of moles of A times RT over V, would be the pressure that it would exert if it were alone, right? So that's the formula for the partial pressure then. Partial pressure of component A is just N sub A times RT over V. So that's the definition of partial pressure. So for example, what are the partial pressures of oxygen and nitrogen in a 25-liter sample containing a mole of O2 and 4 moles of N2 at 300 Kelvin? That's the partial pressure of O2. Moles O2 times RT over V. So what's moles O2? 1.00 moles. And what's our RT over V? R is 0.08206 liter atmosphere per mole Kelvin. And what's our temperature? 300 Kelvin. And what's our volume? 25.0 liters. What do you think the value is of 0.08206 times 300? That should be close to 25, right? That's RT at room temperature. So, what is this number? What is this partial pressure? Okay, so you have 1 times 0.08206 times 300 divided by 25. It's 0.985. So what you're getting? So it's 0.985. 0.985 atmospheres. What's the partial pressure of nitrogen? It's going to be 4 moles of N2. So 4.00 moles times RT over V. What do you think this is going to be? 4 times 0.985, which is 4 times 0.985 is 3.94. What's the total pressure? It's just 5 moles total, right? 1 mole of O2, 4 moles of N2 times RT over V. What do you think this is going to be? 5 times 0.985, or you just add up these two, right? So 5 times 0.985 is 4.925, which is just the sum of the two. So your total pressure is 4.925 atmosphere. So you can see one consequence of the ideal gas equation, if it's valid, if it's applicable, is that the partial pressures will just add up to the total pressure. Okay? So that relationship is known as Dalton's law of partial pressures. If you have a gas mixture, okay, Dalton's law says that the total pressure of a gas mixture is just equal to the sum of the partial pressures of the components. So the total pressure P will just be partial pressure of component A plus partial pressure of component B, and so on and so forth. And it's easy to show that from the ideal gas equation. You can say PV equals N total times RT, right? So what did I do here? I replaced N total by moles A plus moles B plus and so on and so forth. And then what do I do next? Distributive property, right? N sub A times RT over V gives me this one. And N sub B times RT over V gives me this one. Right? But what is N sub A RT over V? That's the pressure that A would exert if it were alone. That's partial pressure of A. N sub B times RT over V, that's the partial pressure of B. That's the amount of pressure B would exert if it were alone in your mixture. So here you can see then that the total pressure is just the sum of the partial pressures of the components of your mixture. So here's an example. If you have an enclosed vessel containing liquid water, the partial pressure of water vapor is called the vapor pressure of water. It's a constant value at a given temperature. In other words, okay, let me just help you visualize this. What would happen if I had a drop of water on a countertop? What happens to it eventually? Evaporates, it disappears, right? But if I have that drop of water in a flask or in a bottle that's sealed, what happens to that water? It stays. What happens there is your water molecules go into the gas phase, but they can't escape the container, so eventually you establish what's called a dynamic equilibrium. The molecules of water go back to the liquid eventually just as fast as the molecules leave the liquid. So it maintains a constant partial pressure in the air above the water. That constant partial pressure of water in the vapor is called the vapor pressure of water. And that depends on the temperature. At room temperature, that's about 23.8 torr. Okay? Now, what would that be if the water was at 100 degrees Celsius, if it's boiling, it's at a boiling point? What would be the vapor pressure of water? That's when it reaches 1 atmosphere. So the boiling point, what we call the normal boiling point of the liquid, is a temperature at which its vapor pressure reaches 1 atmosphere, and that's why it starts to boil. Okay? So at room temperature, the vapor pressure of water is only 23.8 torr. That's kind of low. Right? Now, if the vapor pressure of water, let's say we're at room temperature and the vapor pressure of water in this room is 23.8 torr, we say we are at 100% humidity. We say the air in this room, if the partial pressure of water happens to be 23.8 torr, we say that this room is, the air in this room is saturated with water vapor. That's what happens when outside, for example, when it's about to rain. You say you're at 100% humidity. That means the partial pressure of water vapor in the air is equal to whatever its vapor pressure is. Whatever that vapor pressure is going to be if it were in an enclosed container. Okay? So the actual vapor pressure, the actual partial pressure of water in the air is typically going to be less than that. Okay, so if it's only half of that, we say we are at 50% humidity. So what we call relative humidity, that's just the ratio of the partial pressure of water to the vapor pressure of water at that temperature. Okay? So anyway, if you are in an enclosed container, then you're able to reach that saturation point. Okay? So at 25 degrees Celsius, or 298 Kelvin, the vapor pressure is 23.8. So let's say you did an experiment. Okay, you collected hydrogen. Okay, so this is some water right here. And so you bubbled some hydrogen into your tube that's filled with water. What's going to happen? Hydrogen is going to float to the top and it's going to displace the water. Right? And so what you'll have here is your hydrogen. Okay, so I think you've done this experiment in your freshman lab, right? So you collect your hydrogen over water, and let's say you find that the pressure of the sample is 750 torr. What is the partial pressure of hydrogen there? Well, this hydrogen that you collect is not going to be just pure hydrogen. What else is in there? Water vapor, water molecules in the gas phase, right? So you can say that the total pressure in this particular case is whatever the partial pressure of hydrogen is plus the partial pressure of water molecules in that sample. Well, this is an enclosed sample, so you can saturate it with water vapor. So what would be the partial pressure of water in this case? Whatever the vapor pressure is at that prevailing temperature, which in this case is how much? 23.8 torr. And what is our partial pressure of H2? We don't know. That's the unknown. And what's our total pressure? The total pressure is 750 torr, right? So we can calculate the partial pressure of H2. It's just the total pressure minus the partial pressure of water vapor. So 750 torr minus 23.8 torr. So that should give you how much? 726.2 torr. So we say what we have here, the gas sample that we collect is a wet gas. It's got water vapor in it. And partial pressure of hydrogen in this case would be the partial pressure of what we would call the dry gas. if you subtract the vapor pressure of water from it. Okay. Partial pressure and mole fraction. Let's define mole fraction. Mole fraction, if you're dealing with a mixture, the mole fraction of component A is defined as just the ratio of the number of moles of A to the total moles of the particles that's in your mixture. Okay? So, for a gas mixture, we know that partial pressure of component A is just moles of A times RT over V, right? And the total pressure, we also know, is just the total moles times RT over V. So what would happen if I were to divide partial pressure of A by the total pressure? Then I get number of moles of A times RT over V divided by the total moles times RT over V. Well, T is the same. We're dealing with the same sample. Volume is the same. That sample is just one volume, right? Whatever the volume occupied is by those molecules. So RT over V cancels out. So we can say that partial pressure of A over P is just moles of A over moles total. But what's moles of A over moles total? That's just mole fraction of A. So we can say P sub A over P is equal to mole fraction of A. Okay? Or you can say that partial pressure of A, you can rearrange this, right? So we can say the partial pressure of A is just whatever the mole fraction of A is multiplied by the total pressure. We can generalize this. If you have a component B, then the partial pressure of component B is whatever its mole fraction is in the vapor multiplied by the total pressure. So let's apply that to this problem here. 21% of molecules in a typical air sample are O2 molecules. We say that the mole percent of O2 is 21%, or the mole fraction of O2 is 0.21. What's the partial pressure of O2 in the air sample? In an air sample, if its total pressure is 1.20 atmosphere. How would you do that? Partial pressure of O2 is equal to mole fraction of O2 times the total pressure, which in this case is, what's our mole fraction? 0.21, and our total pressure is 1.20 atmospheres. So what's 1.21 times 1.20 atmospheres? 0.25 atmospheres. Okay. Gastight geometry. If you have change in moles of gaseous reactant or product during a reaction, you can determine that from pressure, volume, and temperature data. Let's look at a case where there's only one reactant or product involved that is gaseous. Then the number of moles of that reactant or product will just be PV over RT. If there's more than one reactant or product that are gaseous, then you're going to have to deal with a mixture of gases. So you'll have to apply Dalton's law to do these types of problems. Okay, so let's look at an example here. Let's say 22.4 liters of carbon dioxide was collected at STP from the decomposition of sodium bicarbonate. So you have sodium bicarbonate, you heated it, you get sodium oxide, water vapor, and carbon dioxide gas. How much sodium oxide was also produced in this reaction? What's 22.4 liters at STP? 1 mole. So that means you've made 1 mole of CO2. So how much Na2O did you make? What's the mole to mole ratio? 2:1. So you say 1 mole of Na2O, sodium oxide, is also produced when you make 2 moles of CO2. So how much? Actually, this is not 1, it's 1.00. 3 sig figs, right? 22.4. So that gives you 0.500 moles of Na2O. And of course, if you know the molar mass, you can just calculate the mass of that. Okay. Here's another example. If you have a strip of magnesium, you react it with HCl, this is what happens. Magnesium will react with hydrochloric acid, will give you hydrogen gas and magnesium chloride aqueous. Let's say you did this experiment. You collected the gas over water as illustrated here. So this is your wet H2, right? And let's say the volume of the gas you collected at 298 K is 2.50 liters. Okay, and the water level in the tube is 10 centimeters above the water level outside. Okay, and the prevailing barometric pressure is 755 torr. And it's at 298 K, and the vapor pressure of water is 23.8 torr. Question is, how much HCl was consumed? Well, you have enough information here to figure out how much H2 was produced. Once you figure out how much H2 was produced, you can figure out how much HCl was consumed. So let's calculate how much H2 did we collect here. What information do I need to calculate number of moles of H2? I'm going to need the partial pressure of H2, the volume of my gas sample, which I know, right? Divided by RT. I know my temperature. What's my temperature? 298 Kelvin. The volume of the gas I collected is how much? 2.50 liters. I know what R should I be using here? This is liters. Might as well express my pressure in atmosphere, right? Yeah, but we don't know the value. We haven't memorized the value of R in torr. So it's easy to change torr to atmosphere. So let's use value of R that's in liter atmosphere per mole per Kelvin. So this is going to be 0.08206 liters times atmosphere per mole per Kelvin. Right. So what remains to be done now is just to figure out partial pressure of H2. How do I know the partial pressure of H2? So here's my sample. This is H2 and water vapor, right? H2 gas and gaseous water. And this thing is 10 centimeters above the liquid level on the outside. And the barometric pressure is how much? 755 torr. Okay. Well, 10 centimeters of water, what's that equivalent to in mercury? You remember? 1 millimeter of mercury is equivalent to how much? 13.6 millimeters of water. So mercury is 13.6 times more dense than mercury. So 1 centimeter of mercury is 13.6 centimeters of water. Okay, that cancels out centimeters of water. And then I change that to torr, which is a millimeter of mercury, which is what? 1 centimeter mercury, it's 10 torr, right? 10 millimeters of mercury is 1 centimeter of mercury. So that cancels out centimeters of mercury. So 10 times 10 divided by 13.6, what would that give me? I think this is 10.0. Yeah, that's 10.0 centimeters. So 3 sig figs. So what's 10 times 10 divided by 13.6? 7.35 torr. So what's the pressure of my gas then? Do I subtract that from 755 or do I add it to 755? can see that my air is pushing on the water harder than the gas is, right? So that means my pressure of my gas is less than my barometric pressure. So my pressure of my gas is 755 torr minus 7.35 torr. What's 755 minus 7.35? 747.65. Keeping in mind that 7 is my last sig fig right there. I only have 3 sig figs in my 755 torr. What's the partial pressure of hydrogen? What's the partial pressure of the dry gas? What would I have to do? Subtract the vapor pressure of water. So it's going to be pressure of the gas minus the vapor pressure of water. And so the pressure of the gas is 747.65 minus vapor pressure of water was how much? 23.8. 23.8 torr. So 747.65 minus 23.8 is how much? $723.85. My last sig fig is this one, right? So I have to remember I only have 3 sig figs. I can defer the round off so I don't build up round off error. So I plug that into pressure of H2, so 723.85. Go back here. This is 723.85 torr. I have to change that to atmosphere. And how do I change torrs to atmosphere? Times 1 atmosphere over 760 torr. Torr cancels out. And so that's the number that goes into your partial pressure. So that's the calculation that you're going to need to do. Once you've known your moles of H2 produced, how do you get moles of HCl consumed? You go back to your balance equation. 1 mole of H2 comes from 2 moles of HCl. So whatever moles of H2 you have, you multiply by 2, you get your moles of HCl. Okay. Now, one application of the ideal gas law is the determination of the molar mass of a gas. Okay? All right. So, to determine the molar mass of anything, it doesn't have to be a gas, it can be a liquid or a solid. All you really need to do experimentally is find a way to find the number of moles and divide the mass by the number of moles. Mass is easy to do, right? Just put it on the balance in the lab, you get the mass. So if you have a way, if you have a sample, you can weigh the sample, get the mass, and you have a way to find the number of moles in that sample. Mass divided by number of moles gives you molar mass. Okay. Now, if the gas is ideal, okay, and you have a way of getting the mass of the gas, and you can measure the pressure, the volume, and the temperature, you can also calculate the number of moles of the gas. So, in order to determine the molar mass of a gas, you need to measure the mass, pressure, volume, and temperature of your sample, and you can get molar mass. So, what will be your formula? Molar mass is equal to mass divided by, what's N? PV over RT, right? So what does that give me? That's M times RT over PV. Okay, so you can use that formula. Now, here's another way we can write this formula. If we know the density of the gas, what's mass divided by volume? That's density, right? So that's going to be equal to density times RT over P. So that's another way you can solve for the molar mass. If you know the density, multiply by RT over P. Now, What if you try to measure the density at STP? Well, RT over P at STP is what? 22.4 liters per mole, right? RT is just V over N. So the molar mass at if you measure the density at STP, whatever the density is at STP, you just multiply it by 22.4 liters per mole. And you get the molar mass. Okay? Here's another way of looking at it. The molar mass is equal to the density at STP times the volume at STP, the molar volume at STP. Well, let's rearrange this. Density at STP is molar mass divided by the molar volume at STP. Isn't that the formula for density? Mass over volume. So in other words, you can get, you're saying that the density at STP is the mass of 1 mole divided by the volume of 1 mole at STP. And we know what this volume is at STP is. What is that? 22.4 liters per mole. And unit for molar mass is grams per mole, right? So you can see mole cancels out. That gives you grams per liter. So if you know the density in grams per liter, you just multiply it by liters per mole. That would give you grams per mole. So this is grams per liter, and this is liters per mole. Okay? The liters cancel out. Density at STP times the molar volume at STP gives you the molar mass. Here's an example. Sample of unknown gas with a mass of 0.8802 contains 0.0200 moles of particles. What's the molar mass of the unknown gas? This is a simple, straightforward question. If you know the mass and you know the moles, how do you get molar mass? 0.8802 grams divided by 0.0200 moles. That gives you molar mass in grams per mole. And that's how much? .001 grams per mole. Okay. Let's try another example here. An unknown gas with a mass of 0.140 grams occupies a volume of 153.1 mils at 373 Kelvin and 1 atmosphere. Okay. Which of these is a possible identity of the compound? This is typically something you would do in the lab. One of the traditional laboratory experiments in physical chemistry is known as the vapor density method or the Duma method. Okay. You put a sample of liquid in a bulb. You immerse it in water. Okay. You heat it up to 100 degrees. So that's 373 Kelvin. So you put it in boiling water. The gas will evaporate. Okay. The liquid will evaporate and the gas will escape. Once all the liquid has vaporized, okay, and most of the gas has escaped, what you do is you seal off, okay, this bulb right here, and then you have a sample of your gas at 1 atmosphere pressure and at 373 Kelvin. And then you weigh that bulb, and then you make corrections for the weight of the bulb before you did this experiment. You have a way to find the mass of the gas. Okay, so the gas that's trapped in there. So this is the Duma or method or the vapor density method for molar mass determination. So what would be the answer to this one? How would we solve for this? Let's solve for the molar mass. Density times RT over P, right? What's our mass? 0.140 grams. Our volume? 153. Let me put this down here so I'll have more room. So, what was the mass? 0.140 grams. Our volume was 153.1 mils. So 153.1 times 10 to the negative 3 liters. I have to make that grams per liter. What's RT over P? It's not 22.4 because we're not at STP. So R is 0.08206. Okay, and that's going to be liter atmosphere per mole Kelvin. And our temperature is how much? 373 Kelvin divided by our pressure, which is 1 atmosphere. So atmosphere cancels out, Kelvin cancels out, liter cancels out. Your answer is in grams per mole. And what does this give you? .140 times 0.08206 times 373 divided by 0.1531. Answer? What's the answer? 27.99. So 3 sig figs, so 28.0 grams per mole. So to answer this question, which could it be? Carbon monoxide, right? Carbon's 12, oxygen 16, that's about 28. Cl2 would have a molar mass of 71, and CH4 is 12 plus 4, 16 grams per mole. So the answer is B. Okay. Then, like I said, that method that we just talked about is called the Duma method, or the vapor density method. You can see that molar mass is just density times RT over P. Okay. So here's a quick question, it's a very simple one. Density of a gas is 3.17 grams per liter at STP. What's the molar mass? Molar mass is density times molar volume, right? What's the density at STP? 3.17 grams per liter. What's the molar volume at STP? 22.4 liters per mole. So liters cancels out. And that gives you 3.17 times 22.4, 71.0 grams per mole. Okay, which of the three compounds we had earlier could this possibly be? Chlorine, Cl2. Okay, ignore trace components and assume that air is only made up of nitrogen and oxygen. What would be the mole fractions of nitrogen and oxygen in air given that its density is 1.29 grams per liter? How do you solve this problem? Well, first of all, from the density, what can you get? The molar mass, right? Is what? 1.29 grams per liter. At STP, that's the density. And what's the molar volume at STP? 22.4 liters per mole. So liters cancel out. That gives you a molar mass of how much? 28.9, right? Okay, how do we figure out how much of that is N2, how much of that is O2? Well, you need to realize that O2 has a molar mass of how much? 32 grams per mole. And N2 has a molar mass of 28.0002 grams per mole. The average, the molar mass here is just a total mass divided by the total molecule. So that's the average for all the N2s and the O2s that are there. If it was all O2, it would have been 32. If it was all N2, it would have been 28. But you're getting 29, right? 28.9. So what do you have more of? Do you have more? What's this average closer to? Is it closer to 28 or 32? Closer to 28. That means you have more nitrogen in your sample than you do oxygen. You can actually figure out because you know how to calculate average, right? So let's just assume you have 1 mole of mixture. Okay? So if we let X be the mole fraction of O2, then moles of O2. If you have 1 mole of mixture and X is the mole fraction of O2, how many moles of O2 do you have? X, right? 1 mole of mixture, you're going to have X moles of O2. How many moles of N2 would you have? 1 minus X. What's the mass of O2? If you have X moles, what's the mass of X moles? X times 32, right? Let's just use 32. And what's the mass of nitrogen? 1 minus X times 28. Right? So what's the total mass? 32X plus 1 minus X times 28. That's the total mass, right? How do I get molar mass? I divide that by the total moles. And the total moles is 1. Now, what's that equal to? Total mass divided by total moles? The average molar mass. So this thing right here is equal to 28.9. Okay? So if that's the case, we just solve for X. So you have 32X plus 1 minus X times 28 is equal to 28.9. Solve for X. And that part is just algebra, right? And you should see that X would be around 0.2, somewhere close to 0.2, 20% oxygen. Okay, air is about 20% oxygen, it's about 70%, it's about 80% nitrogen. In general, you can say that, okay, in fact, this formula is not even specific for a gas. In general, you can say that because masses are conserved, right? So you can say mole fraction of component A times molar mass of component A plus mole fraction of component B times molar mass of component B. That's just the average molar mass. I'm going to put a bar on it so to make it an average. Or you can say, if you have a mixture, the average molar mass of the mixture is the sum of the mole fraction of component I times the molar mass of component I, sum it over all the i's, over all the components. Okay? So that's how you get the average molar mass. Okay. So that ends the lecture for the ideal gas behavior.